back to this episode of the Math Theatre Academy. Today we'll be running through Chapter 3, Pythagoras' Theorem and Surds, and I'll be giving you a brief summary of all the content within the chapter. But to start with, I'm assuming you all know what a right angle triangle is. It has a right angle. Then, when we want to find the length of the hypotenuse, which is the longer side, which we label C, we can use what's known as Pythagoras' theorem. You probably already know this as a squared plus b squared equals c squared. Two shorter sides squared equals the longer side squared, but this is only in a right angled triangle. Obviously, we can use this to solve pretty famous Pythagorean triplets. For example, there's a triplet of 6, 8, and 10. This works because 6 squared plus 8 squared equals 36 plus 64, which equals 100, which is c squared in this case. Therefore, c, which is the hypotenuse, equals the square root of 100, which equals plus minus 10. And in geometry, we just get rid of the minus because there can be no negative length of geometry, so length of the side is equal to 10. Therefore, the Pythagorean triplet is 6, 8, and 10, with the longer side being 10. However, what happens when we don't have a nice rational solution to this? For example, with this right angled triangle here, the equation still holds true with a squared plus b squared being equal to c squared. However, something interesting happens if we try and solve it. 12 squared plus 30 squared equals 144 plus 900. This equals to 1044. This equals to 1044. However, if we pull out our calculator and we try and solve this 1044 square root, we don't get a nice rational solution. It's approximately equal to this number, 32.31. Obviously, if you don't have a calculator though, it can be kind of hard to figure this out. So yeah, I'm just showing here. So in this case, we can just leave it. We can leave the c value as a surd. This surd is something that's underneath a square bracket, like this. Obviously, it's irrational. In this case, surds can't be rational numbers. They can't simplify to something like, the square root of 9 not be a surd because it equals 3. However, in this case, where there's no rational solution, you can use it. You can write it as a surd. Surds can be further simplified, however, and we can show this in our next step. So just some surd rules that you'll want to remember. If you square root a and then square it, or have the square of a inside a square root, it will always give you the a value back. A is representative of any positive integer. Multiplying a squared plus b squared will equal ab squared square root. And multiplying a root of a divided by the root of b equals the root of a divided by b. Just like in algebra, we will write our surds like this, which means 2 times 3. So if it's expressed like 2 3s, it means 2 sets of this 3. And we can actually simplify them by factoring out the perfect squares. For example, here you can see that 12 is broken up into 4 and 3, and we take 4 out of the square bracket by simplifying, because the square root of 4 is equal to 2. So therefore, it's 2 multiplied by 3. And obviously you can put it back in the bracket. You just have to make sure you square it when going back into the bracket. So 2 squared equals 4, and you put 4 back in the bracket, which gets 12. Alright? So here's some questions we can practice. For example, 18. 18 can be broken down into the factors. 9 multiplied by 2. 9 is a perfect square, so we can take it out of the bracket. So it becomes 3 root 2. Here's a bit of a harder one, 108. You can actually, this equals 9 multiplied by 12, which we can break down a bit further actually, because 12 is equal to 4 times 6. So it's 9 times 4 times 3. So this equals, this equals 36 times 3. We can take the 36 out, the square root of 36 is 6, so it simplifies down to 6 times 3. If we want to go back to our original answer here, 1044, we can attempt to break this down into a root as well. Let's just try it here. So the factors of 44 is in 44, so it's going to be a factor of 4. So we can divide by 44. Sorry, not divide by 44, divide by 4. We get 4, the square root of 4, times 261. Taking 4 out gives you 2 times 261. And I believe that 261 is prime. Let me check that now. I just found out that 261 is not prime. We can divide it into 9 multiplied by 29, and then we can take the 9 out, square rooting it, which becomes 3. 2 times 3 gives us 6, and obviously still have the square root of 29, which is prime. So the final solution to this, the final simplification to 1044 square root is 6 multiplied by the square root of 29. Now we can do some more practice on these multiplications and divisions, because within roots they're pretty easy. So we have 15 divided by 3 root 3, which equals this, as can be stated by our formula. It's pretty easy. You just have to remember that root a times root b always gives you root ab, and you can do the same with divide. It's just like dividing, but now it's just under a root. Dividing and multiplying by normal, just under a root. So you have this, which is the same as it all being under a root, which gives you the root of 7. So these are our two divisions. Obviously you can do the similar stuff with multiplication, but the complicated stuff comes in when you're trying to add roots. You can't just, the thing about roots is that you can't just add them together. If you have the root of a number 3, you can't just add 5 and give this 8 like normal addition. No, this is in fact wrong. You have to treat these roots like their own individual variables. For example, if you have root 3, we could assign this value to x, root 5 to y, for example. So, and when you have obviously numbers in front of roots, for example, in this equation, 4 multiplied by the 9 root of 2, this actually just gives us more sense of the root of 2, because obviously you have 9 times 4, so 36, and this is 36 root 2, so the answer to this would be 36 root 2. But see how we are expressing it similar to a variable like x? This is how you kind of got to treat them when adding them together. They have to, obviously you can take perfect squares out of roots in order to like convert them, but these roots need to be treated with care, and they can't just be added together like normal. So for example, if we have this equation here, the root of 8 plus 4 root 2 minus 18. So obviously you have 4 times root 2 here. The thing about this equation is that we can't just add root 8 to root 2. Obviously we have to treat them like separate variables until they have the same number under the root. You can add root 2 plus root 2, for example, and you get 2 root 2. This is your answer here. You don't get a square root of 4. That's not the correct answer, as we discussed earlier. So here we have to try and convert everything to being under root 2, so we can add them together. So in this circumstance, we have 3 multiplied, sorry, not 3, sorry, we have 4 multiplied by 2 plus in a root plus 4 times the root of 2 minus 9 times 2. And now we can take these perfect squares out. So it becomes 2 root 2 plus 4 root 2 minus 2, 3 root 2. Now that they all have root 2's as the values, we can add them together. So 2 root 2 plus 4 is 6 root 2 minus 3. Your final answer is 3 root 2. Correct. Now, here is an interesting equation. Obviously, we can do the same simplification. So we can simplification time. So we go 9 times 3 plus 2 root 5. And we can take all the perfect numbers out by factorizing them. Okay. And we end up getting 3 root plus 5 root 3 plus root 3 minus. However, obviously we can simplify them down, but you see how these are 2 distinct roots? We can't just add them together. We have to keep them separate still. Just like, if they were variables, which is why I told you to treat them like a variable. Obviously, they aren't the same variables. You can still you can convert them and stuff, but in these sorts of equations, you can't just add like root 5 to root 3, for example. And so this is the simplest equation you can get by simplifying the 3's and simplifying the 5's. You get root 3 plus 4 times root 5 as your solution. Multiplication and division of roots is similar to how I structured it previously, with just the roots being multiplied together. And you can actually just take the coefficients of these roots and multiply them together. And same with the division, you can just divide them and have the roots. So, for example, this equation right here, 49 times root 21 divided by 14 times root 3. This just equals 49 divided by 14 multiplied by 21 over 3. So 49 divided by 14, if we take this out, this is just 7 over 2, factorizing by 7. And this is just 21 divided by 3, which is just root 7. And this is the simplified equation to this. Now, when you have these sort of equations where you've got 2 brackets and you have to still use binomial distribution. We taught it earlier as when you have a plus b, a plus d, c plus d. You just have to binomially expand by multiplying a to both c and d, and then b to both c and d, and adding the results together. ac plus d plus bc plus bd. It's just a quick revision on how you binomially expand. So we have to do the same for this situation over here. So we have 3 root 2 multiplied by root 3. Then we have minus 4 root 3 multiplied by 5 root 3. Then we have 3 root 2 times minus 2. And lastly, we have minus 4 3 times minus root 2. Alright, now we can simplify this equation. Obviously you have to expand like I was showing you earlier, multiplying the roots together, multiplying the coefficients, so you get 15 root 6 minus this. As you can see here, it's actually root 3 multiplied by root 3, which is the same as root 3 squared, which we know, based on our formula, gives 3. So it's actually just the coefficients multiplied by 3. So minus 4 is minus 20 times 3, so it's minus 60. And then over here, obviously, look, we've got another pair. So we can actually just minus 6. Okay, so we got, yeah, so it's actually just minus 6. And then over here, we've got one more. The two negative signs cancel out, so it's just a positive. And we've got 4 root 6. So simplifying this all down, we get 19 root 6 minus 60.6. This is our solution to that equation. Now, when it comes to expanding squares, it's quite similar. Remember, your square formula is a squared plus 2ab plus b squared, if we're assigning this to be the a value and this to be the b value. So in this equation, we've got a squared, which is just this squared, minus 3 root 2 times 2 multiplied by 2, because obviously you have the 2ab there, minus, times minus 2 root 3 squared. So in this circumstance, obviously when you have a 2 like this, it actually applies to both. So you end up having 9 times 2, because obviously square root 2 times 2, it's just 18. And then over here, 2 negatives will cancel out here. Well, no, it's not a negative, sorry. It's a positive. My bad, sorry. I made a mistake. It's plus here. So it's just, this all becomes negative because of this value right here. So it's just minus, so it's minus 12 root 6, because obviously you have to factor in this 2 as well, times 2 times 3 is 12. And then finally over here, obviously bring the 2 out to both. Minus 2 squared is just 4, and then 2 squared is, and then obviously that's just 3 because you just expand it, so it's just plus 12. And therefore our solution to this is 30 minus 12 root 6. Now what happens when you have the difference of 2 squares? You just have to remember the same, a similar formula. Remember, it's in the difference between 2 squares, just a squared plus b squared. Therefore, we have root 2 squared plus 3 root 5 squared. This just equals 2 plus, obviously put that there, it's 9, put that here, it's just 5 because it's just expanding out. So 9 times 5 is 45, which is just 47. Now, when we have a fraction like this, we always want to try and express our denominator, the number on the bottom, with a rational solution. So having this just helps in terms of like trying to comprehend this stuff. Obviously here we have a root 2 on the rational denominator. So in order to factor out this root 2 and express it rationally, we'll have to multiply both the top and the bottom by the same value. And in this case, it's going to be root 2, because obviously if you have root 2 times root 2, it just gives 2, which is irrational, which is irrational, sorry. So it becomes 4 root 2 over 2. And we can actually simplify this. This is the benefit of simplifying these equations. So it just becomes 2 root 2. And that is our solution to this. Obviously, if you can try and express these as, rationals, it helps in terms of simplifying these equations and just making life a whole lot easier, especially in cases like these. So here, remember that when we add fractions, we have to multiply root 3 to both the top the bottom of here. We multiply 2 to both the top and the bottom of here. I want to add them together so that they have the same base, or the same denominator. That's what I meant by base. So 4 over root 3 times 2 plus root 3 times 3 is just 3 over root 3 times 2. So we just have here 7 times 2 root 3, and obviously we want to try and get the root 3 out of this denominator, so we're going to multiply both sides by root 3. So in the end, we just have root 3 times root 3, which is 6 times, so not 6, well 6 when combined with 2, it's just 3 times 2, which is 6, sorry. 6 over 7 root 3. And this is the solution to that. Here, I just want to show you how you can do Pythagoras in 3D. Obviously, we can express Pythagorean theorem whenever there's a right angle. So, for example, if we're trying to find the length of A to G, we first need to find this length down the bottom here. We first need to find E to G if we want to find A to G, because we already know the height here is 6, but we need to find this length, which I'm going to call S, and this length here, which is our goal, so I'm going to call D. In order to find S, we need to use Pythagoras, so obviously you have 12 centimeters times 5, so it's just 12 squared plus 5, so 44 plus 25. This equals to 169. In most cases, if it doesn't simplify to a rational equation, you can just leave it as a root in order to multiply for the next one. But here it does simplify, so I might as well just do it. So it's just S equals root 169, because this simplifies to 13 centimeters. So when S equals 13, now in order to find D squared equals 6 squared plus 13 squared, which equals. The reason it doesn't matter if you simplify or not, because here, when you just end up squaring it over here, right? So if we just kept the root 169, if we squared it, it would just equal 169. We're expressing it in this equation right here. So if your root is irrational, say the root of 7, and so just imagine that S was the root of 7. Over here, you could just add 7, because you square the 7, so it just ends up becoming 7 again. And you just add 7 here. So that's why it doesn't really matter when you're doing multiple stages like this, but here I might as well just show you. So obviously, you add 169 to 36, which is 205, I believe. So D equals the square root of 205, which we can actually attempt to find. Take out 5 from this and multiply. It's 21. So it's 5 times 7 times 3. So this doesn't appear, since these are all prime, none of these are perfect squares, and this is the factors of 205. It doesn't seem like we can express this any simpler than the square root of 225 centimeters. We always have to remember to add centimeters because this is the measurement unit. When we have an expression A plus or minus B, there's always a conjugate to this equation, which when multiplied by A plus or minus B, so we'll just imagine the conjugate as A prime. When the conjugate is multiplied to this, it'll always express this root, or if both are in roots, it'll always express this as a whole, as a rational number. So just will always be expressed as a rational number. This is just a symbol for rational numbers, plus or minus. Always will be expressed as a rational number. This is in order to simplify and get rid of the roots, which are irrational, and we can actually use these in several scenarios in order to simplify certain denominators, like these ones. In this instance, we have 2 over 5 divided by 2 over 5 minus 2. So we can actually multiply both by 2 over 5 plus 2. Because as these are the difference of two squares, obviously you do the denominator, you do the numerator, because they start to be equal. As these are the difference of two squares, we'll end up getting a squared plus b squared. And as you can see here, by squaring this and not leaving that, a squared minus b squared. It's always a squared minus b squared. Sorry. By not leaving that annoying 2ab in the center, we actually just get rid of the root entirely from this equation. So here we end up having you expand this across the two brackets to get 4 times 5, which is just 20, because 5 is 5 times 5, 5 root 5, 5, no sorry, root 5 times root 5, which is just 5, as we've explained multiple times now, plus 4 root 5, because it's 2 times root 5. 2 times 2 root 5. And then on the bottom here, as you can see here, difference of two squares, just use this formula. So it becomes 20 minus 4, which is in fact 16. So this is how you can express it without having an irrational denominator. You just use the conjugate of this expression. You just use the conjugate. We can practice some more over here with this one. Root 3 plus root 2 over. Obviously we have multiple different roots here, so in order to get rid of both of them, we just use the conjugate form. So root 3 minus this, and obviously remember we're going to multiply to both sides. 3 equals 18 minus, obviously that becomes 4 times 3, which is 12, over here. Obviously the roots are just being multiplied, so it's 3 root 6 plus minus 2 root 6. So this just becomes root 6 over 6. That's how we express that. When we have, as I was saying before, I was talking a lot about rational numbers. Rational numbers are numbers that can either be expressed as a fraction, so p over q, that have a decimal but they terminate, so 5, 3, 8. See how it terminates and stops going on forever, or that are infinitely recurring but with a systematic pattern that we can predict. So 2, 2, 2, 2, 2 recurring. So this here, obviously this is rational, this terminates, and this is recurring. However, when a number isn't any of these things, we can't express it as a ratio between two numbers, which is what a rational number is, and thus we have to, this number is irrational. For example, we can't express the square root of 2. It doesn't terminate, it goes on forever, it doesn't repeat, it's very unrepetitive, and we also can't express it as the ratio between two numbers. in order to convert some of these in order to convert infinitely recurring to decimals, infinitely recurring decimals to fractions, I'll just show you a quick little trick. So you have 0.2222 recurring. You can treat this as like a variable x. 10x will just be 10 multiplied by this, so you just shift the decimal point one place over. And see now here, we can get rid of the 2222 recurring after the decimal point by going 10x minus x will just give us 2, therefore 9x equals 2, because we just minusing this, so we're minusing this here off of this off of this. So yeah, this just becomes, therefore x, which is what our original solution, which is what we originally assigned this to, x is just equal to 2 over 9. Therefore 2 over 9 equals 0.2222 recurring. Here it's a little more complicated. You have to make sure you eliminate the repetition entirely. So we can't, as it goes 0.12 repeating, we go 1 2 1 2 1 2. That's our x value. Obviously, we can't, if we'd multiplied it by 10, this would be 1.2, 1.2. The digits here, they wouldn't be aligned, so we wouldn't be able to minus this. However, if we multiplied it by 100, we've got 100x equals 1 2 1 2 1 2 1 2. See how these cancel out here? So therefore 99x will just equal 12. Therefore x equals 12 over 99. We can actually just simplify this to 4 over 33. And this is our answer to this equation, expressing it as a rational number. This has been chapter 2. I hope you guys enjoyed. We'll be doing more of these. Thank you.